No security architecture, including operating systems, is totally secure. Every computer system has weaknesses and vulnerabilities. The goal of security models and architecture is to address as many known weaknesses as possible. This is a common goal across many modern operating systems, including Linux or Linux, Unix, Windows, and Apple Macintosh. You see, fundamentally, these OS systems agree that software should not be trusted, although not all software is evil. But protection must be taken to avoid operating system malfunctions and vulnerabilities. This approach is known as the principle of zero trust. We covered this principle in a separate video linked here, which you can refer to for your own reference. Now let's get technical, covering some essential security protection mechanisms, starting with the concept of process isolation. To illustrate this concept, imagine we have a process or program running inside of your operating system, aka your computer screen, of which many simultaneous processes could be running at the same time. For this reason, process isolation requires that the operating systems provide separate memory spaces for each process's instruction and data. It also requires the operating systems to enforce those boundaries, preventing processes from reading or writing data that belongs to another process. Now, to illustrate this concept, let's take the example of physical memory, known as RAM, Random Access Memory, or simply put, memory sticks inside your desktop PC. Now, inside the RAM stick, the logical layer of how this operates at a software layer is very complicated. And there is a lot more to this, which I recommend you Googling. But to start you off, let's look at the logical layout of the physical RAM stick, which is made up of many different blocks which all have their own unique memory address, which references or points to a memory space which is either available or unavailable for a process to utilize. So let's imagine our process running is called Bob, and Bob needs some memory space. The purple blocks indicate space not belonging to any process, so Bob takes some of this space, and the green process, aka Bob, takes over those blocks in memory. And that is how a good process runs in the concept of process isolation. But remember, when a process goes rogue, then what happens when this security mechanism is circumvented? Which means the operating system can no longer confirm the integrity of the process. Again, let's illustrate this concept. Here is a bad bug or malicious process that has affected the computer system and is now affecting memory spaces, including those belonging to the process Bob. This is a serious breach of data integrity and clear violation of security bounds. And here is a CISSP exam note. There is also a concept of hardware segmentation, which is similar to process isolation, but different. Moving on to the concept of covert channels, which is the circumvention of a genuine method or channel that is used to pass information in a way that it was not normally intended for. Using a covert aka secret channel is not easy to detect and may not be protected by the system's security controls because the system thinks the channel is an overt channel, as in it was meant to pass that data through. It does not expect the wrong data to go through that same channel. Furthermore, there are two types of covert channels, a timing channel and a storage channel. Simply put, a covert timing channel modifies a resource's timing in a predictable manner, whereas a storage channel stores data in a shared location where another process can access it. For these reasons, covert channel attacks are very difficult to detect and you must remain vigilant, as a covert channel could be hiding inside an overt channel. Moving on to rootkits, which is a malware that embeds itself deep within an operating system. The term is a derivative of the concept of rooting and a utility kit of hacking tools, where rooting is gaining total or full control over a system, and more dangerously can masquerade as the operating system, so it's very, very dangerous. And the final concept I want to illustrate are more slow, methodical, incremental attacks, of which there are two main types, known as data diddling and the salami attack. So let's dissect these two incremental attacks in more technical detail, with the keynote being that these are slow, gradual increments, aka not obvious attacks, and are prolonged over a period of time without anyone noticing. For example, data diddling is where an attacker makes very small, unnoticeable changes over a period of time without any noticeable change in the data itself, which is where the salami attack comes in, which is more mythical by all published reports and was more financial rooted, but the concept applies to data today. You see, picture a nice piece of salami and a customer wants to buy a piece. So, a butcher, for example, slices a small piece of the salami, but also takes a slice for himself secretly, which over time amounts to one full salami with all those mini slices from other customers paying for the butcher's salami. Another way to think of this is pennies or cents which you steal, which over time adds up to dollars and pounds. FYI for any eagle-eyed viewers, there was a typo which I have corrected. It should have said covert increments. Furthermore, this was a very simplistic video, but there are many other types of design or coding flaws, which I will cover in a separate technical video, just to make you aware. Thank you for watching today's video. I hope you enjoyed the content as much as I enjoyed creating it. If you would like to see more content like this, it would be super fantastic if you could leave a like and subscribe to help support this channel's growth.